Welcome to a brand new deep dive. So I want you to start by picturing a vivid, almost like terrifying scenario.
Oh, this is a fun one.
Right. Imagine you are the lead engineer at a major tech company,
Okay, I'm there.
and you have just spent literally millions of dollars to rent a massive cluster of supercomputers.
We are talking about thousands of the most advanced silicon chips on the planet.
Exactly. All networked together. You can practically hear the server farm humming with electricity, right?
Yeah, and the massive industrial cooling fans are just roaring to keep the hardware from melting.
It's intense. And you are about to hit run on a brand new multi-billion parameter AI model.
The pressure is on.
The entire world, your investors, your CEO, they are all waiting for this big breakthrough.
No pressure at all.
So you take a breath, you initiate the training script, and the process begins.
Here we go.
But then, within the very first 100 steps of training,
Which is, what, barely any time at all.
right, on hardware this fast, that takes maybe 10 to 15 seconds, you watch in absolute horror as the model instantly crashes.
Just completely dies.
It doesn't just fail to learn, it violently slams into a wall of mathematical garbage.
Yep, the dreaded terminal output.
The terminal screen spits out 3 letters. NaN,
N-A-N.
not a number.
Exactly.
It's done.
Not a number. Your millions of dollars, months of architectural planning, instantly reduced to digital rubble before the model even learned to say hello.
It really is the ultimate nightmare scenario for any machine learning engineer.
I can't even imagine the stomach drop.
Oh, you see that NaN on your screen and your heart just drops straight into your shoes.
Yeah.
And what is endlessly fascinating about this specific type of catastrophic failure is that it usually has absolutely nothing to do with the quality of your training data.
Wait, really? Nothing to do with the data?
Nope. And it has nothing to do with whether your core neural network logic is sound either.
So what is it then?
It almost always comes down to a failure in the invisible mathematical scaffolding.
The scaffolding. Yeah, the mathematical structure that holds the entire model together in those incredibly fragile first few moments of its life.
That is exactly what we are getting into today.
The dark arts.
Yes, the dark arts. We've gathered a stack of really dense technical notes, engineering excerpts, and highly specific architectural breakdowns for this deep dive.
And they focus entirely on this invisible scaffolding.
Right. Our mission for you today is to demystify this. We want to figure out what actually keeps a multi-billion parameter AI model from just collapsing under its own massive mathematical weight.
Because it's heavy math. We're going to unpack why these colossal models desperately need to be warmed up.
Right, we'll get into that term.
And how the delicate learning signals, which we call gradients, manage to travel backward through hundreds of layers of computation.
Without just dying out.
Exactly, without dying out or just totally exploding. And we'll look at why seemingly tiny, almost pedantic engineering choices can make or break a project.
We're talking about choices like, exactly where you place a single normalization layer.
Or how you initialize the numbers in a single weight matrix.
These aren't minor details.
No, they're literally the difference between creating a revolutionary, world-changing AI and, well, staring at a very expensive error message.
A very expensive NaN. So whether you are someone who is actively training machine learning models yourself and fighting these battles every day,
Which is a tough job.
or you are just insanely curious about what actually happens inside the black box of artificial intelligence.
We're going to break this all down for you.
We're translating the heavy math into clear, digestible, and hopefully mind-blowing structural logic.
You are going to understand the engineering secrets behind the world's most powerful models.
Let's start at the very beginning. The starting line.
Sub-zero.
Right. I'm looking at our sources, and there is a massive emphasis on a concept called warm-up and another related concept called annealing.
Two very crucial terms.
And I have to say, looking at how this works, the way we teach AI models to learn seems entirely backwards to how humans operate.
It does seem completely counterintuitive, especially if you think about traditional learning or even just basic project momentum.
Right, like if I start a project, I want to hit the ground running.
Exactly. When you start training a massive AI model, the instinctive human thought might be, all right, I have a colossal data set.
Like the entire internet.
Yeah, the whole internet. And you have a massive model with 100 billion parameters.
And tons of compute power.
Right. So you think, let's go as fast as possible right out of the gate.
Naturally, you want a high learning rate so the model takes huge strides through the data and learns quickly.
But the literature in the engineering reality are incredibly clear on this point.
They say absolutely not.
In modern machine learning, particularly with deep transformer architectures like the models powering ChatGPT or Claude.
You have to do the exact opposite.
You're forced to start with a process called warm-up.
Okay, let's define that. Because warm-up isn't just taking it a little bit easy, is it?
Not at all.
The sources define warm-up as starting the training process with a learning rate that is aggressively near zero.
Aggressively is the right word. We're talking about microscopic values like 10 to the negative 7th power.
That is barely a trickle of math.
Barely anything.
And then you gradually, either linearly or on a slight curve, increase that learning rate up to your maximum preset speed over the first few thousand steps of training.
That's the warm-up phase.
Which immediately begs the question, why?
It's a fair question.
If we built this massive machine to learn, why are we putting a governor on the engine and holding it back right out of the gate?
To understand the why, you have to visualize the state of the neural network at step 0.
Before it has seen any data at all?
Exactly. Before it has seen a single word of text or a single pixel of an image. At initialization, every single weight, every parameter in that massive neural network is just a random number.
Totally random.
Engineers literally just pull these numbers from a random distribution.
Yeah.
It is complete, unadulterated chaos inside that model.
It's essentially a brain full of static.
Precisely. Just white noise. And because the internal state is completely random static, the model's predictions on that very first batch of data are going to be staggeringly, hilariously wrong.
I mean, it's not just making a small error, right?
No, it's as wrong as it is mathematically possible to be.
It's guessing, but it's not even an educated guess. It's just random flailing.
Exactly. And the optimization process works by measuring how wrong the model is.
Which we call the loss.
Right, the loss. And then it sends a correction signal, the gradient, backward through the network to adjust those random weights.
But because the initial guess is so monumentally poor,
that initial error signal, that gradient, is massive.
like off the charts massive.
It is wildly huge and completely unstable.
So what happens if you don't do the warm-up?
If you don't have a warm-up phase, if you just hit run with a large normal learning rate right away, that massive unstable gradient acts like a chaotic wrecking ball swinging through the network.
Because the learning rate is basically the multiplier for that error signal, right?
Exactly.
So a huge error times a huge learning rate equals a very violent change.
That's the math, perfectly summarized. It will take those randomly initialized weights and violently shove them into extreme numerical values.
And they just start swinging.
The weights will start to oscillate wildly. In one step, they swing massively positive. In the next, they swing massively negative.
Of just bouncing back and forth.
Very quickly, within a dozen steps, the numbers become so physically large that the computer's memory architecture cannot represent them anymore.
And that's when it breaks.
You get what's called a numerical overflow. The computer throws its hands up, gives you a NAN, and crashes.
The nightmare scenario.
Yeah. Or, in the best case scenario where it doesn't crash.
Which is still bad.
It's terrible. The violent swinging shoves the model into a terrible, deep, local minimum.
Like a bad mathematical valley.
Yeah, and the weights get permanently stuck there. No amount of training will ever pull it out of that ditch.
Wow. I'm picturing this like walking into a pitch black room that you've never been in before.
Okay, I like this.
If you just sprint full speed the absolute second you cross the threshold, you are guaranteed to smash your face into a wall, trip over a table, and break your nose.
That is gradient explosion right there. The network crashing.
Right. So warm-up, in this analogy, is like taking tiny shuffling steps.
Just inching forward.
Yeah, you inch your foot forward a millimeter at a time, feeling for the wall, letting your eyes slowly adjust to the darkness.
You are building a mental map of the room.
And only after you've shuffled around carefully for a minute and your eyes have adjusted.
Meaning the weights have settled out of their completely chaotic, random state into a somewhat stable optimization path.
Right. Only then can you safely start to jog and eventually run.
I love that analogy because it captures the essence of stability. The warm-up phase is exactly that shuffling, eye-adjusting period.
Now, in the grand scheme of a training run that might take months, warm-up is actually relatively short, isn't it?
It is. It usually only lasts for about 1 to 10% of the total training steps.
So it's a fraction of the time.
But it is an absolute lifesaver. You literally cannot train a deep model without it.
Okay, so you warm up, you get your eyes adjusted, and you start jogging.
Right. Once you finally ramp up and reach that maximum learning rate, you might stay there for a bit. The sources call this a plateau phase.
During the plateau, the model is jogging.
It's tearing through the data, extracting all the broad macro-level features.
But you can't jog forever.
No. To get truly high performance, you have to transition into the third and usually longest phase of learning rate scheduling.
Which is annealing.
Yes, annealing, which some people call decay.
And this annealing phase makes up the vast majority of the training time, right?
Something like 90% of the compute is spent here.
So the learning rate is slowly, methodically stepping down, approaching zero.
Exactly.
But here is where the terminology in our sources gets really interesting to me. They make a very deliberate point of distinguishing between decay and annealing.
Yes, they do.
Decay sounds very sterile, very computer science, just making a variable smaller over time. But annealing,
It's a very specific word.
that's not computer science. That's a physical term. That's metallurgy and glass blowing. Why use that specific word?
The etymology there is completely intentional, and it's fascinating because deep learning borrows heavily from statistical physics.
Physics, really?
Oh, absolutely. Think about how blacksmiths or glassmakers work.
Okay.
If you take superheated, glowing hot metal or molten glass, and you instantly plunge it into a bucket of ice-cold water.
Right, quenching it.
Exactly, a process called quenching. It cools way too fast.
What happens when it cools too fast?
The internal atomic structure of the material doesn't have time to organize itself. The crystal structure becomes chaotic, stressed, and incredibly brittle.
Ah, so it breaks easily.
If you drop that quenched glass, it shatters into a million pieces. To make a metal sword strong and flexible, or to make glass durable, you have to anneal it.
So you heat it up and then...
Cool it down incredibly slowly in a controlled environment over a long period of time.
And what is physically happening inside the metal when you do that?
By cooling it slowly, you are giving the atoms the thermal energy and the time they need to shift around, bump into each other, and find their absolute lowest energy state.
So they settle perfectly.
They naturally lock into a perfect, flawless, tightly bound crystal structure. They find true stability.
Okay, I can visualize glowing hot steel. But how does cooling down metal map onto a neural network processing text on a server farm? What is the heat?
In optimization physics, the learning rate is directly analogous to temperature.
Oh, so high learning rate equals high heat.
Exactly. When the learning rate is high, the temperature of the model is high. The system has a massive amount of kinetic energy.
So it's moving fast.
The optimizer is taking huge steps, bouncing wildly all over the lost landscape.
And just to visualize the lost landscape, we can imagine a massive multidimensional mountain range, right?
Yes, with deep valleys, shallow craters, and flat plains. And you want to get to the absolute lowest point in the entire mountain range, the global minimum.
So when the temperature is high, you're just bouncing over the peaks.
Right. And you want that high heat initially during the plateau phase.
Because you don't want to get stuck.
Precisely. If your model gets trapped in a shallow, suboptimal crater, a bad local minimum, a high learning rate gives it the kinetic energy to bounce out of that crater.
And keep exploring the rest of the map.
Yeah. So it prevents the model from settling for a good enough solution too early.
That makes sense.
But as training progresses, you don't want it bouncing around like a pinball forever.
Because then it never settles.
If you stay at a high temperature, you'll constantly jump right over the deepest, most optimal valley without ever settling into it. So you slowly lower the temperature, you anneal it.
Cooling the metal.
Yes. As the learning rate drops, the model's steps become smaller, more deliberate, and more conservative.
So it stops jumping randomly over the peaks.
And starts carefully walking down the slope of whatever valley it's currently in, performing incredibly fine-grained micro-adjustments to the weights.
Until it hits the very bottom.
Until it settles at the very bottom of that specific valley. The atoms have locked into their perfect crystal structure.
That is such a clear visualization. Now, the sources mention a few specific math strategies for managing this cool-down period.
There are a few ways to do it.
They talk about step decay, which just sounds like walking down a staircase.
Yeah, that's exactly what it is. You train for 10 epochs, and then you multiply the learning rate by 0.1. Just a harsh, cliff-like drop.
But the one that seems to absolutely dominate modern AI, the one everybody uses, is cosine annealing.
Yes. Cosine annealing has completely become the industry standard.
Why is that better than the staircase?
Instead of dropping off a cliff, which can shock the optimizer, it follows the smooth, continuous, curved descent of a cosine wave from trigonometry.
Oh, so it's a smooth curve.
It perfectly mimics that physical intuition of a gradual natural cooling process in a forge. It starts decreasing slowly, accelerates the cooldown in the middle, and then very gently tapers off as it approaches zero at the very end of training.
So it's a very natural landing.
Extremely natural.
And there's a brilliant variation of this mentioned in the text that I found totally wild. It's called SGDR,
Yes.
and that stands for Stochastic Gradient Descent with Warm Restarts, which honestly sounds like an oxymoron based on what we just talked about.
It is an incredible technique, and it plays right into the physics analogy we've been using.
How does it work?
With warm restarts, you do the normal cosine annealing. You smoothly cool the metal down. The learning rate drops to almost zero. The model settles into a valley.
Okay, so we're at the bottom.
And then, instantaneously, on the very next step, you spike the learning rate back up to a massive temperature.
You violently reheat the entire system.
You toss it right back into the forge.
Wait, why on earth would you do that? You just spent weeks carefully cooling it down to get the perfect crystal structure. Why throw it back in the fire?
Because of the agonizing reality of the high-dimensional loss landscape. Sometimes, despite your absolute best efforts, the model slowly, carefully settles into a valley that looks really good, but isn't actually the best possible solution in the grand scheme of things.
Oh, so it's a fake bottom.
It's a deep, local minimum, but not the true global minimum. By suddenly turning the temperature back up to maximum, you deliver a massive kick of kinetic energy to the system.
You force the model to jump out of that cozy, suboptimal valley.
And you send it back out to search the mountain range for a better, deeper basin.
It's like having one of those classic Etch-a-Sketches.
Okay.
You draw a picture, you get the sand perfectly settled, but you realize you messed up the proportions. Instead of throwing it away, you just grab it, give it a sharp shake to disrupt the sand, and see if you can draw a better picture the second time.
That is exactly what a warm restart is. It's a controlled shake of the Etch-a-Sketch.
That's brilliant.
And often you'll do this multiple times, saving the state of the model at the bottom of each cooldown, and then maybe combining those different perspectives later.
Okay, so we now have a solid grasp on how engineers control the speed of the model's steps, the temperature of the learning rate.
The warm-up and the annealing.
Right. But what happens to the mathematical signal itself, the actual numbers carrying the error correction as they travel backward from the output all the way to the input?
Ah, the gradient flow.
Because in a deep network, say 100 layers deep, that signal has to travel a phenomenally long way.
It's a long journey for the math.
And that brings us to the whole battle of pre-norm versus post-norm architectures.
This is where we get into the heavy structural engineering.
Let's start with a foundational definition, because I think a lot of people mix this up. The sources talk extensively about the danger of gradient attenuation.
Yes.
But I feel like the term you hear thrown around on AI blogs all the time is gradient vanishing. Are those the same thing, or what is the distinction here?
They are related, but the distinction is crucial for understanding network design. When the literature says gradients are vanishing, it generally implies a terminal fatal state.
Terminal as in dead.
The gradient has literally become mathematically zero. The model is effectively dead.
Wow!
The early layers near the input are receiving absolutely no error signal to update their weights, so they completely stop learning.
So vanishing means the signal flatlined, the patient is dead. What is attenuation then?
Gradient attenuation describes the process of that signal weakening over time. It's the journey towards flatlining.
It's the sickness, not the death.
Exactly. Think of gradient attenuation like a person shouting and that sound traveling through a thick concrete wall.
Okay, I can picture that.
The acoustic energy of the shout isn't instantly destroyed the millisecond it hits the wall.
Ah.
But as the sound waves travel through the dense material, the energy is being absorbed, scattered, dissipated, and significantly weakened.
Right, so by the time it reaches the other side.
It's just a faint whisper.
Yeah.
In neural networks, if the mathematical operations in each layer act like that dense concrete, specifically, if the derivative matrix of the layer has scaling factors less than 1, that gradient suffers a continuous multiplicative loss of energy with every single layer it passes through.
Okay, so what is acting as the concrete wall in an AI model? What is mathematically absorbing our gradient energy?
Historically, in the older generations of AI, it was a few things. The most notorious culprits were the old activation functions, like the sigmoid function or the tanh function.
I remember sigmoid. It gives you that classic S-curve shape, squashing numbers between 0 and 1.
Right. But they are what we call saturated functions. If you look at the calculus, the maximum possible derivative, the maximum signal strength that a sigmoid function can pass backward is only 0.25.
Oh, wow. Only a quarter of the signal.
So every single time a gradient passes backward through a sigmoid layer, it's like driving a sponge into a bucket of water.
Mm-hmm.
Up to 75% of the signal's energy can be absorbed and deleted instantly.
So you pass through 4 or 5 of those layers?
And your signal is basically gone. Other causes of attenuation include overly strict mathematical constraints, where engineers try to force the weights to stay small, which ends up unintentionally starving the network of gradients.
Making the walls thicker.
Yeah. And frankly, just having a very deep straight tube network without any alternate pathways will naturally attenuate signals just through the sheer friction of repeated matrix multiplications.
But the sources highlight a massive architectural battle that specifically deals with this attenuation problem in modern transformer models.
The great debate.
The battle of post-norm versus pre-norm. And reading through this, it's all about one seemingly trivial decision. Where exactly do you place the layer normalization relative to the residual connection?
To understand why this matters so much, we have to visualize the architecture.
Let's do it.
A transformer block has a main pathway. Think of it as a massive, multi-lane highway running straight through the model from beginning to end. This is the residual stream.
Okay, the main highway.
Then, at each block, there is an off-ramp. Data takes the off-ramp, goes into a complex sublayer like the self-attention mechanism or the feed-forward network to do the heavy lifting and reasoning.
So the complex work happens off the highway.
Exactly. Then, the output of that sublayer takes an on-ramp and gets mathematically added back onto the main highway.
Okay, I have that image. The main highway and the side roads where the work happens. Let's unpack the old way first, the way they built the very first transformer in 2017, post-norm.
In a post-norm architecture, the data goes down the main highway, takes the off-ramp into the attention sublayer, gets processed, and emerges back onto the highway via addition.
Right.
And then right after that merge, right on the main highway itself, you place a layer normalization block.
Hence post-norm. You normalize the data after the fact, after it has merged back together.
Exactly. And the sources detail how this specific, intuitive arrangement creates a fatal mathematical flaw during backpropagation.
Which is when the learning signal is traveling in reverse down the highway.
Right. Because the layer norm is placed directly on the main highway, acting on the combined signal, its job is to normalize the variance of the data.
Sounds innocent enough.
But when you run the calculus backward, that variance normalization acts exactly like that thick concrete wall. It severely attenuates the gradient as it tries to move from the deep layers back to the shallow input layers.
So every time the gradient hits a post-norm block on the highway, it gets weakened.
Every single time.
The sources reference a Stanford University presentation that actually measured this attenuation physically in a model, right?
Yes, and the data from that Stanford presentation is incredibly revealing. It's a stark visualization of the problem.
What did they find?
They looked at a post-norm setup right at initialization. They measured the expectation of the gradient norm, basically the raw size of the learning signal, at the very last layer of the network, layer 6 in their small example.
Okay, at the very end.
And at layer 6, the gradient is massive. It's an absolute beast of a number.
Huge signal.
But as that gradient struggles backward through those post-norm layers, getting normalized over and over, it gets crushed. By the time that signal reaches layer 1, the input layer, the gradient is tiny, almost microscopic.
Wow. So you are left with this extreme, wildly unbalanced gradient landscape across the model.
Completely lopsided.
You have massive, violent updates happening at the end of the network and virtually no learning happening at the beginning.
Yes. And wait, this connects perfectly back to our first topic.
The warm-up.
Exactly. This unbalanced landscape is exactly why post-norm architectures absolutely demanded a warm-up phase.
Oh, go. I see it now.
The connection is direct.
If you have a massive beast-like gradient waiting at the final layer and you hit it with a high learning rate on step 1 without warning, the model instantly blows up into nans.
The massive update shatters the final layer's weights.
So warm-up is the literal mandatory lifesaver you need to artificially clamp the learning rate down, holding it near 0.
To give the network time for those variances to stabilize. And for that massive final layer gradient to calm down to a reasonable size. That's precisely the dynamic. If you try to train a post-norm network without a warm-up phase, it is guaranteed sudden death.
But then, as the field matured, researchers realized they could fix this without relying entirely on the warm-up crutch.
They made a tiny, almost imperceptible change to the code.
What did they do?
They moved the layer normalization off the main highway and put it inside the off-ramp right before the data enters the attention sublayer. This is pre-norm.
So the main residual pathway, that central highway of the network, is now completely clear of any normalization checkpoints.
There are no toll booths on the highway anymore.
The highway is totally clear.
Yes. And mathematically, this seemingly minor shift changes everything about how the network learns.
How so?
By clearing the backbone, when you calculate the derivative for backpropagation, the math simplifies in this beautiful, elegant way. The derivative of that clear highway pathway becomes an identity matrix.
An identity matrix, which in linear algebra is denoted as I.
Exactly.
Okay, we are going to talk a lot about the magic of the identity matrix later, but for anyone who hasn't taken linear algebra recently, an identity matrix is basically the matrix equivalent of multiplying a number by 1.
That's exactly it. If you multiply any matrix by the identity matrix, it just equals itself. It remains completely unchanged.
So in our highway analogy, the identity matrix is a perfect, frictionless, lossless conduit.
It means the gradient signal from the very last layer can flow backward along that main backbone highway 100% losslessly.
Yeah.
It completely cures the gradient attenuation problem.
That is incredible.
And again, the Stanford data from the sources confirms this physically. In a pre-norm network at initialization, the size of the gradient at layer 1 is almost exactly the same as the size of the gradient at layer 6.
The signal is completely balanced, gentle, and stable from end to end. The concrete wall is gone.
It is entirely gone.
Okay, but this raises a huge contradiction in the text, and I need to stop and ask you to clarify this because it seems totally illogical to me.
Okay, lay it on me.
The sources clearly state that pre-norm fixes the gradient attenuation issue. It balances everything out. The backbone is an identity matrix, and therefore, theoretically, a pre-norm architecture mathematically does not need warm-up to survive step 1.
Mathematically true.
But then, a few paragraphs later, the text explicitly points out that the engineers training the biggest, most advanced models today, like GPT-4, Llama 3, DeepSeek, these massive models in 2026, they are all using pre-norm architectures.
Right.
But they are still using a warm-up phase. Why? If pre-norm cured the disease, why are these genius engineers still forcing the patient to take the medicine?
It's a brilliant question, and it highlights the friction between pure theoretical math and the gritty reality of practical engineering at scale.
Ah, theory versus practice.
You're completely right. Theoretically, pre-norm doesn't need warm-up to prevent that initial gradient explosion. The math is naturally stable. But the role and purpose of warm-up evolved as models got vastly larger.
How did it evolve?
It went from being a mandatory lifesaver to a very necessary insurance policy.
Insurance against what? If the gradients are stable, what is going to break the model?
It's insurance against two modern realities of scaling AI compute. The first reality is massive batch sizes.
Batch sizes. Okay.
Back in the day, we trained models on a few dozen sentences at a time. Today, we train models on hundreds of thousands, sometimes millions of tokens in a single forward pass, a single step.
That's an incomprehensible amount of data hitting the model at once.
Right. And in the very early stages of training, when the weights are still somewhat random, dumping a massive batch of diverse, complex data into the model introduces intense, chaotic statistical noise into the gradient calculation.
So the signal is stable in size, but messy in direction.
Exactly. Even with pre-norm balancing the scale of the gradients, that sheer volume of noisy, contradictory data can cause violent directional swings in the learning path. Warm-up gives the optimizer time to slowly aggregate reliable statistics from these massive batches before it starts taking large, confident strides.
It's like trying to find the average opinion of a crowd. If you listen to 3 people yelling, you get a bad average. You need to slowly survey the crowd to find the real trend.
That's a great way to put it.
Okay, what's the second reality?
The second reality we need insurance against is the physical hardware limits of low-precision math.
Hardware.
To save memory and compute faster, modern training uses formats like FP16 or BF16 16-bit floating point numbers.
Instead of the standard 32-bit.
Exactly. And 16-bit numbers have a very, very limited numerical range before they max out. A 16-bit number can only hold a value up to about 65,000.
That's not very high when we're doing billions of calculations.
It's really not. If an unexpected noisy spike occurs early in training, which happens all the time with huge batches, it can easily push a gradient value past 65,000.
And then what?
If that happens in FP16, it instantly overflows to NAND and your model crashes. Warm-up acts as a physical safety buffer, keeping all the numbers artificially small to respect those strict 16-bit hardware limits until the model stabilizes.
So, to summarize, post-norm warm-up is a mathematical lifesaver against explosion. Pre-norm warm-up is just incredibly robust, safe engineering practice to handle noise and hardware constraints.
You nailed it.
Wow. Okay, so we've established that post-norm architecture suffered from these dangerously massive gradients at the end of the network. But I want to drill down into the math of that
I'll just
explosion.
get into the math.
How massive is too massive? The sources introduce this core mathematical concept called gradient expectation, denoted by a capital letter E. Let's really explore this because it seems foundational to everything. What exactly is gradient expectation?
A gradient expectation, or E, is a statistical concept. It represents the expected norm, or the average statistical size, of the gradients during initialization or the very early chaotic stages of training.
So it's basically the average size of the signal.
Think of it as a measurement of how much energy or force the learning signal currently holds. And the absolute, uncompromising golden rule of deep learning optimization is this. At initialization, E must be meticulously managed.
The sources are emphatic on this point. If your gradient expectation E is greater than 1 at step 0, it is a catastrophic failure.
Absolutely catastrophic.
Right, but why? This is where my intuition breaks down. The number 1 is not a very big number. Why is an E of, say, 1.3 considered an absolute disaster that will ruin a multi-million-dollar training run?
It comes down to the terrifying power of the multiplicative effect in deep networks.
The multiplicative effect.
The entire process of deep learning backpropagation relies on the chain rule from calculus.
Yeah.
And in the context of neural networks, applying the chain rule essentially means performing a continuous, unbroken chain of matrix multiplications, layer by layer, from the output back to the input.
Okay, so you take the gradient at layer 100, multiply it by the weights at layer 99, multiply that by layer 98, and so on.
Exactly. Now, if the average gradient size, the expectation E passing backward through each of those layers, is strictly 1.0, then 1 times 1 times 1 remains 1. The signal is perfectly preserved.
Right, that's safe.
But if E is even slightly greater than 1, let's use your example 1.3, that number gets multiplied by itself over and over and over as it travels backward.
Oh, I see exactly where this is going. It's compound interest.
Yes.
So that instead of growing your bank account, it's compounding your errors.
That is a perfect analogy. It is malignant compound interest. If you have a relatively standard, modern transformer model with 64 layers and your initial E is 1.3, the size of the gradient by the time it reaches the early input layers isn't just 1.3 times 64.
It's 1.3 to the power of 64.
Yes, 1.3 to the 64th power.
And doing the rough mental math, 1.3 to the 64th is something like 20 million.
It's roughly 19.5 to 23 million, depending on the exact variance, yes.
Good Lord.
So a signal that starts off looking totally fine, just slightly too large at 1.3, silently multiplies into an apocalypse of 20 million times its intended size by the time it reaches the bottom of the network.
The gradient violently explodes.
And this doesn't just cause basic numerical NaN errors. It fundamentally and irreparably breaks the optimization software itself.
Specifically, it destroys the Atom optimizer, which is the industry standard tool everyone uses to update their weights.
Let's talk about Atom, because I feel like the optimizer is the unsung hero or villain of AI training.
We always talk about the model architecture, but the optimizer is the actual engine doing the driving. Why does an exponentially exploding E greater than 1 wreck the Atom optimizer so badly? How does Atom actually work?
Atom stands for Adaptive Moment Estimation. It is incredibly sophisticated. Older optimizers just took the gradient, multiplied it by the learning rate, and updated the weight. That's simple gradient descent.
Pretty straightforward.
Atom doesn't do that. Atom looks at the history of the gradients. It calculates what we call moments. It tracks the running average of the gradient's direction. And crucially, it tracks the second-order momentum, which is the running average of the squared gradients.
Okay, wait, what does tracking the squared gradients actually do for the optimizer? Why bother?
Tracking the squared gradients gives Atom a measure of the variance or volatility of that specific weight. Atom uses this variance to create a bespoke, custom step size for every single parameter in the network. If a weight has historically had huge volatile gradients, Atom automatically shrinks its step size to be careful.
Oh, that's clever.
If a weight has tiny, consistent gradients, Atom boosts its step size to speed things up. It normalizes the learning process.
That sounds incredibly smart and stable.
It is brilliantly stable, once it has a history. But here is the fatal flaw. At step 0, Atom has 0 history.
Right.
Its internal memory buffers tracking all that momentum and variance are completely empty. They're initialized at 0.
So what happens when that 20 million hits it?
If you hit Atom on step 1 with an incredibly massive, incredibly chaotic gradient because your E exploded 20 million, Atom essentially panics.
It has no context to realize that 20 million is a bad number.
Exactly. The math of Atom divides by the square root of that momentum buffer. Because the buffer is empty and the new gradient is massive, the math breaks down. Atom maximizes its step size immediately, and it applies maximum unmitigated force to the weights in a completely random direction dictated by the noise of the first batch.
I picture the entire process like this. Imagine you are building a massive, intricate skyscraper. You spend months carefully pouring and leveling the concrete foundation. You measure everything to the millimeter.
The foundation is key.
In this analogy, that foundation is your careful mathematical weight initialization. Everything is perfectly balanced, ready for construction. And then on day 1 of building, before you've even put up a steel beam, a massive magnitude 9 earthquake hits.
Go.
That earthquake is an E greater than 1 update from an empty atom optimizer. The perfectly leveled foundation is instantly pulverized into rubble. You've completely destroyed the delicate starting state of the model before it even had a chance to learn what a token is.
That is a brutally accurate visual. You have effectively scrambled the brain of the network before it could think. The signal-to-noise ratio is completely backwards. You have massive chaotic noise permanently destroying a delicate architectural signal.
But hold on, this creates a fascinating mathematical paradox. And to be fair, the sources address this head on, but I want you to walk me through it.
Let's hear it.
If an E slightly greater than 1, like 1.3, explodes exponentially to 20 million, shouldn't an E slightly less than 1 just vanish to absolute 0?
That's a great question.
Like the Stanford data we talked about earlier show that the pre-norm architecture has a gentle E of about 0.2. If you multiply 0.2 by itself 64 times, you get a number so infinitesimally small it's basically invisible. Why doesn't the pre-norm architecture suffer from catastrophic gradient vanishing? How does the signal survive?
This is where the absolute brilliance of the residual connection truly shines.
The highway.
Right. We mentioned earlier that prenorm moves the normalization off the main highway, leaving it clear. The mathematical operator that connects the off-ramp back to the main highway is simple addition. It's literally just x plus the sublayer output of x.
Just simple addition, not multiplication.
Yes. And when you run the calculus backward through an addition operation, the backward pass becomes an addition of gradients, not a multiplication.
So the gradients aren't multiplying 0.2 times 0.2 times 0.2 down the chain.
Exactly. The main highway, the backbone, maintains that pristine identity matrix on you. Because it's an identity matrix, it carries a healthy, perfect gradient expectation of exactly 1.0 all the way from the output to the input. It never degrades.
And what about the side roads?
The sublayers, the attention mechanisms on the off-ramps, they receive their gentle, heavily suppressed gradient of 0.2, but because they are connected via addition, those 0.2 gradients are just added to the main signal, not multiplied against it. They don't have to multiply with each other across 64 layers.
So the main highway stays at a perfectly healthy size, carrying the core truth of the error backward. And the sublayers safely siphon off a gentle 0.2 update to adjust their specific weights without blowing up the optimizer or vanishing into nothingness.
That's the elegance of it. It's a mathematically perfect solution to the exponential trap.
It really is beautiful when you see the logic behind the equations. Now, we've been talking a lot abstractly about these matrices multiplying and adding, gradients flowing like water. But I want to physically ground this.
Okay, let's get physical.
I want to look at the actual physical operations happening on the silicon chips inside that server farm that makes all this calculus possible. This brings us to a really dense part of our sources: tensor contraction and the INSUM operation.
Oh, INSUM.
Before we look at the code, what exactly is a tensor contraction?
If you truly want to understand what an NVIDIA GPU or a Google TPU is actually physically doing for 90% of the time during an AI training run, you have to understand tensor contraction. To put it simply, it is the high-dimensional, leveled-up big brother of standard matrix multiplication.
Okay, matrix multiplication I remember from high school algebra. You take rows of one flat grid of numbers, you multiply them by columns of another flat grid, and you add the results up to get a new grid.
Right, that's a 2D operation, rows and columns. But in modern deep learning, we almost never deal with simple 2D matrices. We deal with tensors.
What's a tensor?
A tensor is just a container for numbers, but it could be a 3D cube, a 4D hypercube, or even a 5D array. A tensor contraction is when you take two of these massive high-dimensional tensors, you look for axes or dimensions that are the exact same length, you multiply the matching elements along those specific axes, and then you sum them all up.
So you are multiplying and then summing.
Yes, it's formally called a sum product operation. And crucially, when you sum across an axis, that axis contracts or completely disappears from the final output shape.
So if I have a 3D block of numbers, like a Rubik's Cube, and another 3D block, I can mathematically contract them along their depth axis, and the result isn't a new 3D block. It might just be a flat 2D grid, because the depth was summed up and compressed.
Exactly, you've compressed the higher dimensions down. And this sum product operation is the absolute beating heart of AI compute.
Everything runs on this.
Whether the model is calculating attention scores to see which words relate to each other, or running data through the feed-forward networks, or doing image convolution, over 90% of the raw mathematical operations in these massive models are just gigantic tensor contractions.
That is wild.
It is so fundamental to the physics of AI that hardware giants like NVIDIA with their tensor cores and Google with their specialized TPUs don't build general-purpose chips anymore. They physically hardwire their silicon architecture at the transistor level, specifically to perform this exact sum product contraction as fast as the laws of thermodynamics allow.
That is mind-boggling. So if this is the core physical operation of the entire industry, how do software engineers actually write the code for it? Because writing out nested loops for 5D matrix multiplication sounds like a fast track to madness.
It would be a nightmare.
The sources introduce a tool, a function in PyTorch, called einsum, which stands for Einstein Summation Convention. Now, putting Einstein in the name of your code tool sounds incredibly intimidating.
It definitely sounds intimidating, and when you first look at the syntax, it looks like alien hieroglyphics. But once you understand it, einsum is actually the ultimate elegant cheat code for expressing incredibly complex tensor math.
How so?
In traditional frameworks, if you want to multiply multidimensional tensors, you have to chain together this confusing, unreadable mess of reshape, transpose, squeeze, and map-mul commands. It's error-prone and hard to read. Einsum allows you to bypass all of that.
What does it look like?
It lets you write a single, short string of lowercase letters that perfectly mathematically describes the exact contraction you want the hardware to perform.
Okay, to make this concrete, the sources provide a very specific and, according to the notes, slightly terrifying example of an einsum bug. I'm going to read the exact line of code. At model weights equals torch.einsum parenthesis, single quote, bhnd, comma, bhmd, arrow nm, single quote, comma q, comma k, end parenthesis.
Oh boy.
Okay, looking at that string of letters, BHND, comma, BHMD, arrow NM. It looks like a typo. Let's break this down piece by piece. What is happening here?
Let's decode the letters because they tell a very specific story.
Yeah.
Q and K are our two input tensors. In a transformer, these represent the queries and the keys in the attention mechanism, basically. The model asking, what am I looking for? And the data saying, here is what I have.
Right.
These tensors are four-dimensional. The first string of letters, BHND, represents the 4 dimensions of the Q tensor.
What do the letters stand for?
B stands for batch size, how many sentences we are processing at once. H is the number of independent attention heads. N is the sequence length, how many words are in the sentence for the query. And D is the feature dimension, how many numbers represent a single word. So BHND defines the shape of Q.
Got it.
The second string, BHND, defines the shape of K. It's exactly the same, except M represents the sequence length of the keys.
Okay, so we have a 4-dimensional tensor interacting with another 4-dimensional tensor. The hardware is lining them up. Then we have an arrow, followed by the letters NM.
Right. The arrow specifies what the final output tensor shape must look like. The output is just NM, a 2-dimensional matrix consisting only of the sequence lengths.
Wait a second. Where did BHND go? We started with batch head and feature dimension, and they completely vanished from the output.
This brings us to the ironclad rule of einsum, which is the most important thing an engineer can memorize. If a letter appears on the left side of the arrow, but it does not appear on the right side of the arrow, the operation will automatically multiply and then sum up all the values along that entire dimension. It will crush it out of existence.
Okay, I can understand summing up D. In an attention mechanism, you always do a dot product across the feature dimension D to get a single score of how much two words relate. That's standard math. But summing up over B and H, summing up the independent batches and the independent attention heads.
Exactly. That is the horror of this specific line of code. By omitting B and H on the right side of the arrow, this single line of code violently, indiscriminately mashes all the separate independent batches of data together.
Wait, what does that mean in practice?
It takes sentence A, sentence B, and sentence C and just adds their numbers on top of each other. And it takes all the independent attention heads, one head looking for grammar, another looking for emotion, and violently adds them all into one single flat 2D grid.
Is that code brilliant, or is it completely broken? Why would anyone deliberately compress all their distinct, carefully separated data batches like that?
According to our sources, there are exactly 3 scenarios where you would see this specific violent contraction code in the wild. Scenario A is purely academic visualization.
Okay, making graphs.
Let's say a researcher writes a paper and wants to generate a cool global heat map to see, on average, across their entire 1 million document dataset, how tokens relate to each other. Maybe they want to prove that the model always pays attention to the very first token in a document. To get that macro-level average, they would intentionally sum over the batch and the head dimensions to squash all the data into one single global perspective graph.
Okay, that makes sense for drawing a pretty graph in a research paper. What's the second scenario?
Scenario B is found in highly advanced theoretical physics. PyTorch isn't just used for AI. Physicists use it. If you are simulating quantum mechanics or complex tensor networks, those dimensions might not represent independent batches of language data. They might represent physical degrees of freedom in a quantum system, like spin states, that physically need to be summed and contracted over to calculate the global state of the system.
Okay, quantum physicists get a pass, but what if I'm just an engineer at a startup trying to train a language model and I accidentally write that code?
Then you are in scenario C. You have written a massive, silent, day-ruining code bug.
You emphasize silent. PyTorch won't pop up a warning and tell me I'm actively crushing all my distinct sentences together.
Absolutely not. PyTorch is a mathematical engine. It assumes you, the engineer, know exactly what you are doing. If you write that ANSYM string, PyTorch will execute it perfectly, incredibly fast on those tensor cores. It will sum everything up and spit out an n by m matrix just like you asked. It will not throw an error. You will not crash.
But the data.
But your AI model is now receiving entirely corrupted, overlapping, meaningless data. Sentence A is bleeding into sentence B. It will silently ruin your entire training run, and you might spend weeks staring at a loss curve that looks like random garbage, pulling your hair out, trying to figure out why the model isn't learning, totally unaware that one missing letter B in a single line of code destroyed your data.
That is terrifying. It really highlights how much absolute, rigorous control engineers need over the exact shape and scale of their data at every step. One typo and the geometry collapses, which is the perfect bridge into our next major topic, taming the wild numbers.
The numbers get very wild.
We need to talk about the concept of normalization versus standardization and why a highly specific technique called RMS norm has basically taken over the entire AI industry. Let's start by clarifying the terminology because the sources practically beg us to fix this, noting that even senior engineers constantly confuse these two words.
It is a chronic endemic source of confusion in the machine learning industry, and it causes endless headaches. Let's define them strictly. Normalization, which is formally called min-max scaling, is a mathematical operation that forcefully squashes all of your data points into a strict, rigidly predefined box.
Yeah.
Usually, it forces every number to sit between exactly 0.0 and exactly 1.0.
Okay, squashed into a box.
Standardization, which is formally called z-score scaling, is a completely different mathematical concept. It shifts the data so that the average value, the mean, is set at exactly at 0, and the variance, the spread of the data, is scaled to 1. Crucially, standardization does not enforce any strict upper or lower limits.
So to visualize this, min-max normalization puts the data in a rigid steel cage. Nobody gets to be bigger than 1.
Right.
Standardization just asks the data points to stand in a neat, orderly formation around 0. But if one data point really needs to be a 5 or a 10, it's allowed to step out of line. Why is min-max, the rigid steel cage, considered a terrible idea for modern AI architectures?
It fails completely because of how it mathematically reacts to extreme outliers. In massive neural networks, especially deep transformers using attention mechanisms, you frequently get severe numerical spikes in the data activations.
Like sudden surges of data.
Imagine you have a layer processing 1,000 tokens. 99.9% of your data points are hovering peacefully around a value of 0.1. But suddenly, because the model recognized a highly critical keyword, one single token activation spikes to a value of 100.
A massive outlier disrupting the peace.
Exactly. Now, if you apply min-max normalization to that layer, the algorithm is forced to accommodate that massive 100 within its strict 0 to 1 box. So it assigns the value of 100 to equal 1.0.
Right.
But to maintain the relative scale of the data, it has to aggressively crush all of those perfectly healthy, useful 0.1 values down to virtually 0, something like 0.001.
Oh, wow.
Because of a single isolated outlier, the algorithm was forced to essentially delete all the useful variance, all the subtle feature resolution. in the rest of the data. The network goes blind to the nuances.
That's a disaster. It's like taking a beautifully detailed photograph, but because there's one bright reflection from the sun, the camera darkens the entire rest of the image until it's just black silhouettes. You lose all the data.
Exactly.
So the industry obviously uses standardization instead, but the confusing part, and what the sources point out, is that the most famous, ubiquitous technique used in transformers is called layer norm, which is explicitly a standardization technique.
Yes. It's incredibly frustrating nomenclature. Layer norm uses the mean and the standard deviation to center and scale the data. It is absolutely, mathematically, undeniably a standardization technique.
Why call it norm?
The industry got sloppy with the terminology about 10 years ago, and now everyone just calls everything norm out of habit. We say batch norm, layer norm, RMS norm. They're all technically standardization.
Okay. Glad we cleared up the vocabulary. So layer norm was the old standard, but our sources spent a massive amount of time dissecting a newer variant called RMS norm root mean square normalization.
The new king.
And they state unequivocally that this is the new king. This is what giants like Meta use for Llama 3, what DeepSeek uses, what powers the cutting edge. What exactly is RMS norm doing differently from the classic layer norm?
RMS norm was born out of engineers taking a long, hard, critical look at the complex math inside traditional layer norm and asking, do we actually need to do all this computation?
Lazy engineers make the best tools.
True. Layer norm does two main things. First, it calculates the mean of the data and shifts everything so the mean is 0. Second, it calculates the variance and scales the data. This first step, the shifting process, requires computing and storing a specific learnable bias parameter, usually denoted by the Greek letter beta.
Okay, the beta shift.
The inventors of RMS norm ran experiments and realized a shocking truth. The shifting part, the centering of the mean around 0, doesn't actually contribute meaningfully to the stability or the success of the model's training.
Wait, really? So they just deleted half the math equation?
Literally, they took a red pen to the math. RMS norm completely drops the mean calculation, and it completely drops the beta shift parameter. It purely, exclusively focuses on scaling the magnitude of the vectors using the root mean square of the values.
And what's the benefit?
The result of dropping half the math. You have fewer parameters to store in memory, and the computational speed of that layer increases by 10% to 50%, with virtually zero loss in final model accuracy.
Okay, faster compute and less memory usage is the holy grail of engineering. I get why they use it, but the text goes deeper. It compares RMS norm to another scaling technique called scale norm, which is based on the L2 norm. And the math comparison here gets really sticky, so I need you to walk me through it slowly. The text claims that RMS norm and L2 norm are mathematically nearly identical.
They're essentially mathematical siblings. They both measure the total energy of a vector by squaring the elements, adding them up, and taking the square root. The only difference is what they do with the dimension of the vector, denoted as d.
Like the width of the network.
Right, think of d as how wide the network is, maybe 4096 or 892 neurons wide. The L2 norm calculates the total absolute energy. If the dimension d grows wider, the total L2 norm naturally grows larger with it. RMS norm, however, calculates the average energy density. It explicitly divides the sum by d before taking the square root.
So if you look at the raw algebraic formulas, they are literally only separated by a constant mathematical factor of the square root of d.
Exactly. One has the square root of d division, the other doesn't.
Okay, this is where I need to step in and express some serious skepticism about the engineering logic presented in these sources.
Go for it.
If RMS norm and L2 norm are fundamentally the exact same mathematical operation, just separated by this simple constant square root of d, why on earth do we need to invent a specialized RMS norm operator in our node? Every normalization layer has a learnable scaling parameter called gamma. The optimizer adjusts gamma to scale the layer's output perfectly. Why don't we just use the mathematically simpler L2 norm and let the incredibly powerful atom optimizer just learn to multiply the gamma parameter by the square root of d? Why go through the effort of hard-coding that division into the physical architecture of the model?
I love this question because this right here is perhaps the deepest, most profound insight into AI engineering wisdom in our entire deep dive today.
Really?
You are mathematically, theoretically 100% right. Given enough time, the atom optimizer could absolutely learn to scale the gamma parameter by the square root of d. It has the capacity to do that math. But relying on Atom to do that structural scaling is a catastrophic trap.
Why is it a trap? We just talked about how Atom tracks variance and creates bespoke step sizes. It's supposedly this magical adaptive mathematical engine.
Remember what we discussed earlier about Atom's critical vulnerability in the first 100 steps of training?
The empty buffer.
Yes. At step 0, when a model is initialized, Atom is blind. It hasn't stabilized its momentum buffers. Now imagine you use the simpler L2 norm without the square root of d correction. As your modern model gets wider and wider, say you increase the dimension d from 1024 to a massive 8192, the raw mathematical output of that L2 layer shrinks dramatically. The energy gets diluted across that massive dimension.
So the output signal coming out of the layer gets tiny.
Yes, and consequently, during backpropagation, the gradient flowing back to update that specific layer's gamma parameter also shrinks proportionally. It becomes microscopic.
Okay, so the signal is weak.
So put yourself in the optimizer's shoes.
Yeah.
In the exact moment when Atom is most vulnerable, blind, struggling to establish its momentum and find the right direction in the dark, you are handing it a microscopic, heavily diluted gradient signal and essentially saying, hey, I need you to figure out that you need to scale this value up by a factor of 90 immediately, or the model crashes.
That's a tall order.
It physically cannot do it. The parameter updates will be excruciatingly slow, Atom will fail to adjust in time, and the model will either stall out completely or explode into nans.
So by forcing the optimizer to solve a purely structural scaling problem, you are distracting it while it's also trying to survive the chaos of initialization and learn the actual features of the data.
Precisely. You are giving it an impossible dual task.
Yeah.
And this leads to the prevailing fundamental philosophy in modern AI architecture design. Let gods be gods and Caesars be Caesars.
That's quite a phrase.
Scaling factors that are related strictly to the physical dimensions of the network, like the width d or the depth L, those are structural realities. They're deterministic math. You should hard-code that structural math directly into the operation itself, which is exactly what RMS norm does by physically including the division by d in its core formula.
Taking the burden off the optimizer.
By hard-coding it, you present a clean, perfectly scaled, dimension-immune signal to the optimizer, right from step one. You liberate the optimizer. You let the optimizer focus only on learning the semantic features of the data, the grammar, the logic, the facts, and you stop forcing it to fight the physical geometry of your architecture.
Let gods be gods and Caesars be Caesars. I absolutely love that framework. Give the optimizer the absolute easiest possible starting point. Handle the physics so the brain can learn. And that obsessive, almost paranoid desire to perfectly tee up the optimizer leads us to our final section, the ultimate goal.
The Holy Grail.
We're talking about a concept called identity mapping and the pursuit of the perfect blank slate.
If there is a holy grail in neural network initialization, an absolute theoretical peak that engineers strive for, it is identity mapping. Mathematically, it is expressed with the simplest equation possible. F of x equals x.
Meaning whatever data goes into a layer comes out exactly the same on the other side.
Yes. At step one of training, before any learning or weight updates have happened, you want the data to flow through a multi-million parameter computational layer completely, utterly unchanged.
Now, I have to play devil's advocate here. Why is doing absolutely nothing the highest pursuit of advanced AI architecture? If my multi-billion-dollar model just spits out exactly what I put into it, it's not a very good AI. It's just an expensive mirror.
It's a great point, but you have to separate the end state from the beginning state. It's not about the model doing nothing at the end of training. It's about the model doing nothing at the very beginning.
Okay, why?
Let's go back to our discussion about gradient attenuation and the terrifying threat of exponential math compounding 1.3 to the 64th power. If your neural network layer acts as a perfect identity mapping, its derivative for backpropagation is the perfect identity matrix, I go. As we said, multiplying an identity matrix by another identity matrix 1,000,000 times still equals an identity matrix.
Oh, right, the lossless conduit.
It creates an infinite survival channel for your gradients. The learning signals can travel infinitely deep into a network without vanishing to zero or exploding into billions.
Okay, that protects the backward pass, the learning signal. What about the forward pass, the actual text or image data moving through the model?
It fiercely protects the data too. Think about what goes into a language model. The input is a human language token, a word like apple or democracy, that has been mapped to a mathematical embedding vector. That specific embedding vector contains precious, fragile semantic meaning.
So you don't want to mess it up.
If every random, chaotic layer in a 100-layer network twists, scales, and rotates that vector even slightly, by the time that data reaches layer 100, the meaning of human language has been churned into unrecognizable, random white noise.
Like a game of telephone gone horribly wrong.
Exactly. Identity mapping ensures that at step one, the pristine original signal of the input data reaches every single part of the network perfectly intact. It gives the optimizer a flat, smooth, safe basin to start exploring in, rather than dropping it on the side of a jagged mathematical cliff where it's immediately blinded by noise.
Okay, the logic is sound. We want a perfect blank slate. But how do we actually build this physical reality in code? How do engineers force millions of random weights to equal f of x equals x at the start?
It's not easy.
We already saw that the prenorm architecture helps naturally suppress the sublayer output because the variance denominator acts as a large dampener early on. But what about the other massive components? What about the feed-forward network, the FFN, which contains the bulk of the model's parameters?
The FFN is a tricky beast.
Here is what seems like a totally brilliant, obvious idea to me. If we desperately want the derivative to be an identical matrix, and we want f of x equals x, why don't we just initialize the weights of the FFN to be literal identity matrices? Just hard code the I matrix directly into the weights at step 0. Why mess with random numbers at all?
It is a very intuitive leap. It seems like the most elegant solution, but the sources specifically and systematically shut this idea down. Initializing the feed-forward network with perfect identity matrices is mathematically impossible, and even if you could fake it, it would be fatal to the model for three distinct, deeply technical reasons.
Really, mathematical impossibility.
Reason number one is purely a matter of dimensional geometry. An identity matrix, by its strict mathematical definition, must be a square matrix, meaning it has the exact same number of rows as it has columns. It maps the space to itself. But an FFN in a transformer doesn't use square matrices.
What does it use?
It projects the data up to a massive hidden dimension, say, expanding a 4Z96 dimensional vector out to a massive 16384 dimensional space, and then a second matrix projects it back down. These are rectangular matrices. An identity matrix mathematically does not even exist for shapes like that.
Okay, the rigid geometry of linear algebra defeats my first idea, but let's play make-believe. Let's say, theoretically, there were square matrices. Let's pretend we altered the architecture. Would it work then?
If you alter the architecture to use square matrices, that brings us to reason number two, which is a foundational core concept in both physics and deep learning. Symmetry breaking.
Symmetry breaking.
If you initialize a neural network layer with a perfect, pristine identity matrix, every single neuron in that layer is perfectly symmetric to every other neuron. When the loss is calculated and the gradient flows backward because they are symmetric, every single neuron will receive the exact same mathematical update.
And if they get the same update, they learn the same thing.
Exactly. They will all learn the exact same feature. You might have 10,000 neurons in a layer, but they will all act like one giant redundant neuron. The network loses all diversity of thought. It becomes mathematically brain dead.
So you need chaos to be smart.
You must have random noise in your initial weights to break the symmetry so that each individual neuron gets a slightly different gradient, goes off on its own path, and learns something slightly different from its neighbors.
So a perfect I matrix is actually too perfect. It makes the network a monolithic block instead of a diverse brain.
Okay, what is the third reason my idea fails?
The third fatal flaw is the activation functions. Inside the FFN, sandwiched right between those two rectangular projections we talked about, you have a nonlinear activation function. Usually this is something like a ReLU, which stands for rectified linear unit, or a GELU.
Let's look at ReLU. ReLU looks at a number, and if it's positive, it lets it pass. If it's negative, it aggressively chops it to exactly 0. So even if you magically created a rectangular identity matrix that somehow magically broke symmetry, the second your data hits that ReLU function, statistically half of your values are instantly destroyed and turned to 0.
Just wiped out.
The perfect f of x equals x mapping is instantaneously shattered by the activation function itself.
So my brilliant idea is geometrically impossible, creates brain-dead monolithic neurons, and gets chopped to tiny pieces by the ReLU function. Fair enough. I concede. But that leaves a massive question. What is the actual industry solution then?
They get creative.
If we know we need an identity mapping to survive initialization, but we absolutely cannot use identity matrices, how do the engineers at OpenAI and DeepMind get that perfect blank slate?
They use a brilliant, highly tuned mathematical compromise. They use random weights to ensure symmetry is broken, so the brain is diverse. But they apply what is called a scaled initialization.
Scaled initialization.
Specifically, they take the random weights of the final projection layer of the FFN, and before training even begins, they divide all of those weights by a specific mathematical factor, the square root of 2 times the total number of layers in the network.
Oh, okay, wait. If L is a really big number, like a 100-layer deep network, you are dividing those weights by a massive number.
Exactly. You are severely squashing those weights down so their values are incredibly infinitesimally close to zero. They're still technically random, so symmetry is preserved and broken properly, but their overall magnitude is so tiny that the actual numerical output of the FFN is effectively something like bank 0.00001.
Almost nothing.
When you take that tiny output and you add it back onto the main highway via the residual connection, so the math is x plus tiny noise, the result is virtually functionally identical to x. You have mathematically achieved a noisy but highly effective identity mapping.
It's an illusion of an identity mapping.
It is. Alternatively, some of the very newest modern architectures actually skip the scaling and just use literal zero initialization on that final branch. They just set the weights to literal zero, making the branch output exactly zero, and they blindly trust that the optimizer will eventually nudge those weights from zero and break the symmetry on its own later in the training process.
Trusting the atom optimizer.
But whether they use scaled or zero initialization, both methods achieve the exact same architectural goal, making the complex sublayer whisper so quietly at step one that the main signal can pass through the highway completely undisturbed.
Okay, let's take a deep breath. We have covered an absolutely incredible amount of ground today.
We really have.
We started by looking at the violent, chaotic birth of a multi-billion parameter model and how the warm-up phase acts as a gentle, mandatory ramp to prevent the whole thing from violently tearing itself apart.
Shuffle in the dark room.
We explored how moving a single normalization block pre-norm versus post-norm and striving for identity mapping literally paves an unobstructed, lossless highway for gradients to flow backward through hundreds of layers without vanishing or exploding exponentially.
No more concrete walls.
And we saw how hyper-specific, seemingly pedantic mathematical choices, like dropping the mean calculation in RMS norm or dividing by the dimension d, are designed solely to save the atom optimizer from doing impossible guesswork in the dark.
It really is a staggering marvel of human engineering. The sheer volume of knowledge, the thousands of hours of trial and error, and the deep mathematical intuition covered in these sources represents the collective genius of the entire global AI community over the last decade.
It's so impressive.
By taking the time to understand these concepts, the necessity of warm-up, the physics of attenuation, the terrifying power of an Einstein bug, the elegance of RMS norm, you are looking far past the media hype. You are seeing the actual physical structural math that makes the world's most powerful AI models function.
You now know the literal secrets inside the black box. But I want to leave you with a final, slightly provocative thought to mull over as you go about your day.
I love a good final thought.
We have just spent this entire deep dive talking about all this incredible architectural genius, pre-norm, RMS norm, identity mapping, cosine annealing, and it is all designed, fundamentally, to do one single thing: to trick these massive, complex models into starting as a perfect, undisturbed blank slate.
That's the goal.
We are engineering unbelievably complex mathematical scaffolding just to make the network forcefully do nothing at step one. But as AI scales aggressively from billions of parameters to trillions, and the networks get hundreds of layers deeper, will we eventually hit a hard physical wall where even these brilliant tricks fail?
It's a scary thought.
Might the next major paradigm-shifting breakthrough in artificial intelligence not be a new way to process language or images, but an entirely new, undiscovered mathematical language for how we initialize the void?
It's a profound question, and it's what keeps researchers awake at night. We are constantly fighting the natural entropic chaos of high-dimensional mathematics, and eventually, the current scaffolding might need to be completely torn down and reinvented.
Something to ponder. Because the next time a team spins up a $20 million supercomputer cluster and hits run, we definitely don't want it to hit a wall of garbage.
We want it to wake up smoothly and start learning.
Thanks for joining us on this deep dive.